So back in 2022, a paper came out of Google that completely changed the game for scaling AI. See, it wasn't just about making models bigger anymore, it was about making them smarter. Let's break down the incredible idea behind switch transformers.
You know, for the longest time, the rule in AI was pretty simple. If you wanted a smarter model, you just made it bigger. But that whole approach was leading us straight towards a massive wall. It just wasn't sustainable. So the big question became this: how can you get 1,000 times more power without paying 1,000 times the price? That is the exact puzzle the switch transformer was designed to solve.
All right, so to really appreciate just how genius this solution was, we first have to get our heads around the problem. And trust me, it was a huge one that was threatening to slow down the entire field of AI.
The rule of thumb in AI was, well, it was pretty straightforward. If you wanted a model that could do more, you just scaled it up. You added more parameters. You can think of those as the neurons in the model's brain. You fed it more data, and you threw more computing power at it. And hey, for a long time, this worked like a charm. Models like GPT-2 and T5 were proof that just getting bigger was a pretty reliable way to get better. But here's the catch. That approach is brutally inefficient. Seriously, think about it. It's like having this giant, all-knowing brain, but to answer a simple question like, what's the capital of France, you have to fire up every single neuron you have. It's just a colossal waste of energy. The cost to train and run these dense models was getting insane, creating this very real scaling wall. So the researchers behind switch transformers took a step back and proposed a totally different way of thinking. Instead of one giant brain trying to do everything, what if you could have a team of specialists?
And this right here, this is the core idea. On the one hand, you've got the old way, the dense model, that one giant brain we just talked about, where every part of it lights up for every single thought. But on the right, you have the mixture of experts model, or MO. This is totally different. It's like having a dedicated expert for history, another for math, another for poetry, and you only call on the one you actually need. This is the whole idea behind a sparsely activated model.
Okay, but how does the model know which specialist to talk to? Well, that's where this key piece of the puzzle comes in, something called the router. Think of it like a really smart traffic cop. For every little piece of information that comes in, we call these tokens, they can be a word or even part of a word, the router takes one look and says, yep, you're a math problem, go see the math expert, or, this one's definitely for the poetry expert. It actually learns how to send the traffic to the perfect specialist for that exact job.
Now, the whole mixture of experts idea wasn't brand new. People had tried it before, but the models were kind of complex and often unstable. What the switch transformer paper did was introduce a ridiculously simple, almost counterintuitive idea that just changed everything.
Yeah, and this quote, right from the paper, tells the whole story. The conventional wisdom at the time was that to get good results, you had to send each token to at least 2 different experts. But the switch team basically asked, what if we just don't do that? What if we make everything way simpler and just pick the single best expert? That one little decision was the key that unlocked the whole thing.
So let's just walk through how this works because it's so elegant. Step 1, a token comes in. Step 2, the router looks at it and figures out which single expert is the best fit. Step 3, that token gets sent or switched over to that one expert and only that one expert. And here's the magic part. Step 4, all the other experts, they just sit there, totally inactive, saving an unbelievable amount of compute power.
And this diagram from the paper just shows it perfectly. You can see the token for the word more comes in, the router sends it over to, say, expert 2, then the token for parameters comes in, and the router decides, nope, you're going to expert FFN1. And notice how all the other experts are just dark, sitting there not doing anything. The model is absolutely massive, but the actual path that each token takes is tiny and super efficient.
Okay, so simplifying things sounds nice in theory, but what did it actually do for performance? Well, the results were, frankly, they were staggering. Let's just look at the data here. See that line on the bottom? That's the T5 base model, a really powerful dense model. Now look at the lines above it. Those are the switch transformers. Look at how much faster they climb. To get to the same level of quality, the switch model gets there in a tiny fraction of the time.
So how much faster are we talking? 7 times faster. I mean, think about that. Let's say you have a budget to train an AI model. With the switch architecture, you could hit your target in just 1 day, while the old dense model would still be chugging along for a full week. This wasn't just a little improvement, it was a total game changer.
And that, right there, is the ultimate payoff. Because they solved this massive efficiency problem, the switch architecture just blew the doors wide open for scale. All of a sudden, the idea of a model with over 1 trillion parameters wasn't some sci-fi dream.
It was a real engineering challenge that this paper proved we could actually tackle. So why do we still talk about this paper today? It's because its central idea, that you can get incredible performance by only activating a tiny specialized piece of a giant model, has pretty much defined the frontier of AI ever since. Now, of course, it wasn't a perfect silver bullet. It's always important to talk about the trade-offs. This new architecture created some new engineering headaches. You had to worry about load balancing, making sure the router was giving all the experts a fair amount of work. Training could also be a bit more unstable, and now you had communication costs between all these different experts to deal with. These are the kinds of challenges researchers are still trying to perfect.
But the impact? It's absolutely undeniable. When you hear people talking about incredibly powerful and efficient models today, like Mixtral, well, you're looking at a direct descendant of the switch transformer. The mixture of experts idea that it made practical is now a cornerstone of modern AI.
And that leaves us with a really fascinating thought to end on. The switch transformer taught us a huge lesson. The future of AI might not just be about who can build the biggest model, but about who can be the most clever with the power they have. It's about architectural intelligence. And it kind of makes you wonder, what's the next big, inefficient thing in AI that's just waiting for its own brilliantly simple solution?